It has come out well.
Yeah, yeah.
It's neatly we did with all
arranged. Yeah, nice. Nice work. Yep.
check பண்ணி பாத்தியாப்பா லைவ் ஸ்ட்ரீம் ஒர்க் ஆகுதா மொபைல்ல போட்டு பாரு இப்போ கேமரா வந்துருச்சா வந்துருச்சு
Oh, okay. Okay. Okay, while the system is coming up, I want to talk to you guys about, in general, so I mentioned yesterday that today's lecture is dedicated to geotechnical investigation. And so most of the geotech, because it's underground, sometimes, okay, you cannot see, so you have to use non-intrusive, non-destructive testing methods, okay, and most of those are what we call the geophysical testing method, okay, and so it takes a lot of not guesswork but analysis method, okay, and so from an inverse engineering perspective, okay, geophysics, because you don't know what's underneath, the interpretation of the results is heavily dependent on your knowledge of the location, what has been done to the site. Okay, for example, if there's any underground coal mine, okay, and what kind of rock formation. Is it limestone? Is it mostly shell or some other kind of minerals? Even how the area is formed. Okay, so you get into an area where it's very inverse problem, okay, and much more than the structural perspective. So this is a cicada tree, okay, it's the oldest tree in the world, okay, and so this one is the Smithsonian just published the oldest tree ever, okay, 16 million years old. Do you know how they count the age of the tree? You go by the rings, right? Yeah. So if this is 16 million years, somebody must have spent a lot of time counting the rings, okay? Which is not easy. The reason is because as the trees grow older, many things they will experience, okay? A superstorm that may bring part of the trees down, and then they regrow from the bark, the stem. And so you can see from the history of this tree many things that happened in the past, okay? And there are people who doesn't believe that, the earth is that old, okay? But if we believe in the tree ring counting method, okay, that should be very consistent, okay? But even so, 16 million counting throughout this tree is a very complex process, okay? And so the based on the rings of a tree, for a very simple young tree, it is a very consistent process, okay? Because you know why they have, they go through every season, so the new cells dies out, and then they push further and further, right? And so for a very young tree, that principle works pretty good. But when you go to a tree that old, it gets very complicated, okay? And so I imagine many people will probably argue about this 16 million year, okay? I mean, 16 million, that take a long time to count, right? And many times you count wrong, and yeah. So this is the kind of things that we need to recognize when we do geotechnical investigation. And geoforensics are actually cross-domain, okay? So, of course, geotechnical, geomechanics, right? Dam failures, retaining wall failures, all these are categorically defined. But then you may be getting into areas where like geological engineering, okay? So geological engineering are actually real discipline offered in some schools in the United States, okay? And those are people who may be involved in natural landmark like landslides, okay, slope stability problems, or even mining, collapse, subsidence, and so forth, okay? And then there's more recent geoenvironmental, okay? So it deals with man-made environmental structures that, such as landfill, okay? So landfill has a lot of problems. So investigation of landfills is falls under geoenvironmental area, okay? But you also have other cross-discipline, such as mining, especially underground mining. A lot of times when you open up a hole in the ground, okay, it becomes a natural process for groundwater to seep in. Okay, so groundwater flows underground, but whenever you have a cut in the path of the groundwater, the pressure differential will cause groundwater to seep out. Okay, and then you have what we call the pool water problem, and that can be environmental, because if you're in a coal mine, the water may become acidic, okay, and then the water flows back into the groundwater, then you become an environmental problem. Okay, people will be drinking from this acidic groundwater. Okay, so you quickly realize that in geotech alone, there are a lot of cross-domain expertise involved. Okay, and then so again, going back based on the description of the mode of geotechnical failures. Okay, so all these are geotechnical. So you see the definitions are probably familiar to most of you. Okay, settlement problem, stability problem, bearing capacity failures, lateral earth pressure for retaining wall. Okay, so retaining wall can be structural, can be geotechnical. Okay, because especially if it's a reinforced structure, you know, the failure of that can be due to the soil pushing or the stability of the, so active or passive pressure failure should be a job that's structural and geotech combined, okay? And then you have soil yielding problems, unanticipated static and dynamic loading, earthquake, okay, or foundation vibration problems and so forth, okay? And then ground uplift. Ground uplift is usually because of either buoyancy, such as if you build a structure on a lake or in a lake. Okay, so the hydraulic pressure may become a uplift. But we also seen some of the light structures, you know, light foundation structures that may be lifted due to other mechanisms, such as soil suction. Okay, so you quickly realize that uplift is a very significant problem, which is not common, but it happens. Okay, drag down is the reverse of uplift. Okay, so the soil suction literally pull the light structure, lightweight foundation downwards. Okay, and then liquefaction, and then leachate is more a geoenvironmental type of problem. Okay. Bad chemicals, heavy metals that seeps into the groundwater, okay, groundwater contamination and so forth. So we already have ground uplift up there, okay, and then the geotechnical systems are usually harder to quantify. Okay, so we know retaining wall, we know dams, we know bridge foundations, abutments, and so forth. Okay, and within it also separates into deep foundation and shallow foundation type. Okay, so from a profiling perspective, geotech can be categorically distinguished into those different types. Okay, tunnels is a very special area. Okay, so but tunnel can vary. Okay, so I investigate a particular tunnel project, but then you know the DOT actually claimed that is a bridge. So it was really an overhead culvert that, you know, you have cars passing on the top and then you have cars passing underneath. So depends on your perspective, it's a tunnel and it's a bridge. Okay, so you have those kind of very unique systems. Okay, so keeping in mind the definition of any of those are based on perspectives. And there are some failed underground systems, especially unique is piping. Okay, so sewer lines or underground pipeline, and in the U.S. now there are a lot, especially the introduction of Google Fiber. So for higher speed internet, we do a lot of and those are short-term constructions. Okay, so actually one of the problem with roadways and highways is not so much failure of the system, but the failure because of trenching. They have to dig the holes on the side of the road. And every time that you have to disturb the soil on the existing roadways, you will immediately introduce a problem that will subside. Okay, a typical cycle is within 3 years you will see the pavement cracking. Okay, and those are very expensive to repair, but it's still relatively cheaper than repave the entire roads. Okay, so those are critical techniques that issues that you have to keep in mind. Okay, and then as I mentioned, groundwater fluctuations or variations. Groundwater is dynamic. Okay, they don't always stay the same profile, and so anytime that you, especially in the region, you have heavy constructions, you will cause the groundwater table to change. Okay, and that fluctuation may bring slope failures and different kind of ground problem. Okay, so those are critical issues. And then in this day and age, most of the time, especially in the city, you are very likely to be built on top of a old construction. Okay, so you may be building on top of a landfill or a residential area that the soil is actually disturbed. Okay, and so as a result, there will be failures. But the failure, if you only know about the natural condition of the soil and not knowing the history of the site, then your diagnostics may be wrong. Okay, so those are critical issues to recognize. I wanted to show you some case studies from the Philippines. Okay, so in the Philippines, after Haiyan, we went on site and we see a lot of coastal erosions. Okay, and so this is a sea wall that was breached because of very strong waves. Okay, and so for doing this analysis, but of course this could also happen when the concrete seawall was eroded over time. Okay, so going back and trying to determine how much was the force actually forcing the wall to collapse is a very challenging work. Okay, and so this kind of analysis, you have to know the existing structure, how it was built, and so forth. Okay, and then of course the erosion of this beach area becomes a really critical issue. Okay, so beach erosion, especially in the tourist environment, okay, can be a very lucrative job for civil engineers. Okay, because it's not common. Okay, but you have to remember this itself is a system. Okay, so when you involve in this kind of projects, you need to know, how was the beach built. Okay, there are a lot of artificial beaches. Okay, so I remember growing up, we go to Thailand for vacations, and then I was sitting on the beautiful white sand beach, and then my hand was digging, trying to build a castle. Little kids do that, and then I suddenly found plastic sheets underneath. Those are geotextiles. And so you realize that, wow, even this beautiful, seemingly natural beach is not so natural, okay? And it's actually an engineered system. So underneath the white sand, you have geotextiles that protects erosion of that beach, okay? So knowing all this, then you know how to design, especially when the system fell, okay? Like how much the the resistance, the frictional resistance of the geotextile was designed originally. Okay, so those are critical issues, and whether it was pinned. Okay, so geotextiles are usually nailed to the natural soil. Okay, so all these are critical elements when you deal with the erosion problem. And then coastline erosion, again, this is a extreme case. Okay, so you have all these erosions due to heavy waves. Okay, impact, and usually it's very difficult for you to assess the impact. But you can see that the erosion is into the grassed area, and all this, the loss of the soil and stuff can be costly to the owner of this site. Okay. And then this is a highway pavement that was being built over another eroded area. Okay, so you can see from the paved area, know that this place has been disturbed. Okay, so it's not an ideal site for you to do any kind of assessment. Okay, and then more scouring, and actually highway pavement damage. Forensic can be a challenging work because you may not be able to see this, but there was a heavy sewer pipeline built underneath the highway. Okay, so the idea is to drain the water from that side into the ocean. Okay, but when you have this kind of impacts, then the damage of the whole system will happen. Okay, and then natural slope failures. Okay, so for this kind of analysis, you wanted to know what was the soil saturation, where was the groundwater before the storm and during the storm, so that you can do the slope stability analysis, and also which kind of analysis technique needs to be done. Okay, so all these are more related to geotech. Okay, and then some scouring such as this. While it is, obvious, it is difficult to determine whether this system is actually stable. Okay, so how much was the damage to the system becomes critical. And also, when you come here and then do the assessments, how much of this was happening due to daily storm? Okay, is another area of forensic interest. Okay, so when you look at a site, it is really important for you to have a holistic approach to the assessment. Okay, so you look around not just for that problem area, but you also have to work around. So we work around this area. This is only about maybe 10 meters from the actual wave, the beach area. But when we walk into the further into the compound, we actually found even more erosions, another 10, 20 meters in. So what happened here is this kind of scouring actually is more due to the storm surge. In other words, the wave may impact and scour, okay? But there's another kind of scour is when the water sustained a long time over the area, and then when the water withdraw, it actually takes a lot of materials with it, okay? And that kind of force, it's kind of like a suction force. It's actually very significant, and it will not happen right away, okay? Storm surge usually take hours to subside, kind of like a tsunami, okay? So those are the critical elements to recognize. Okay, then geophysical investigation. Okay, so this is a building, had nothing to do with coastal area. Okay, but it's a building next to a pond. Okay, and so for this particular building, they actually found sinkhole within the building or near the building. So how can we prevent the sinkhole from continue to happen? So one of the theory that the geotechnical company is doing the repair work is that they believe the groundwater fluctuation from the lake, the lake water is not always level, but it's so close to the building that the seepage into underneath the building actually caused the erosion. Okay, and so one solution to this, and this is one of the few cases where I actually involved in the repair of a existing engineering problem. So to resolve this, the company Bate engaged us to determine. So their solution to solve this problem is actually build a grout curtain. In other words, they will inject concrete and then creating like an underground concrete wall so that the seepage will not attack to the building foundation anymore. Okay, and so this is the grouting mechanism. So they would drill a big hole and then they pump concrete into the ground. Okay, and so the injection of grout would require you to know where would that curtain wall be. Okay, so you need to know where is the seeping of water coming from. So this is the scenario. So this is the pond. Okay, I have to backtrack. So actually, before we were engaged, they don't really know how the sinkholes were formed. Okay, and so before they decide to grout, these are the sinkhole areas. Okay, so we did several geophysical testing. So you can see we did the surface wave testing, 1 area, 2 area, 3 area, 4, 5, 6, 7 around the building. Okay, so basically wanted to see what is the geological setting of that area looks like. Okay, and so you can see from test 1, 2, I just demonstrate 1, 2, 3 because 1, 2, 3 is surrounding on the exterior of the system. So notice that the analysis actually would tell the same testing method actually tell you different things. Okay, so
how do you make these boreholes, Professor? You go by machine drilling? Or
yeah, machine drilling. Yeah, yeah. They drill and then they use the same hole to inject. Yeah. So the 1, 2, 3, 4 test actually tells you the rock formation because they are outside of the building, right? And then the 5, 6, 7 actually tells you the foundation condition. Okay, how much sinkhole was forming and how bad it is. Okay, so from the outside test, just showing you test 1, 2, 3, you notice that 1 and 3, the bedrock is shallow. Okay, and 2, the bedrock is higher. Okay, the competent rock, I should say. Okay, so 2 is here, and then 1 and 3 are actually on the 2 opposite sides to the pond. Okay, and after talking to the geotechnical engineers and so forth, we decided.
So you mean to say from that graph,
yeah,
the soil profile, the topography is changing.
Right. Yeah.
Between these two.
Yes. Yeah. So we believe that 2 and 3. I mean, yeah. No, 1 and 3 involve more sinkhole. Yeah, and then 2, in that direction, there is no sinkhole. Yeah, and that's how we so 2 is around here, and then 1 and 3, right? So this is where they decide to build the concrete grout because they believe the groundwater, the runoff is this direction, but the seepage damaging to the erosion. Yeah.
Because of the pond location, we get this sort of effect.
Right.
As the days progress,
right, it seeps into.
And,
yes. Yeah.
Seepage.
Right. Yeah. It caused the soil to subside. Yeah. And so this is where, at the end, where they did the grout curtain. Okay. So this is the kind of analysis that you would do and benefit from. Now, as I mentioned, so this is an aerial image, and Harit asked me a lot about this. So all these indentations on the ground surface is all because of the underground mine subside. Okay, and this doesn't happen overnight. It happens over years. Okay, so a common practice in the U.S. in the old days, 70s, 60s, and even earlier, is once you excavate the mine, you leave it, you just close the mine, so people don't go in there and play, okay? But you don't go and backfill all the mines, okay? And so this is the problem in the future, okay? So you will see the surface subside. And these are the lucky cases. You actually see the surface indentation. There are some of the mines, you know, you own the property, but you don't see on the surface that there are actually mine collapse. Okay, and so those are the ones that are dangerous.
But as per the government rules, we are supposed to refill
No,
it and...
no, you're not. Yeah, you don't have to backfill. Yeah, I mean a lot of these old mines before the government has any policies. Yeah, even today we don't do that. So I was explaining last night. The mining. There are two mining techniques. For those, okay. One method is called the room and pillar. Okay, so room and pillar method, you dig into the mines and then you leave chunks of concrete as pillars to support the structure. Okay, and the mining engineers are usually the one that study. In fact, we recently have a paper published, so we review all the design techniques, you know, and unfortunately many of those are not conservative enough. Okay, so you imagine over time, as I mentioned, groundwater will seep in, start eroding those columns, and so from the side view, you have the roof, okay, and then this is the room, and this is the pillar, okay. So if the overburden pressure starts to pushing down, and if the roof is not strong enough, it will collapse, okay. And more likely is this actually start give away because you have a strong stress concentration here. Okay, and so the columns would actually buckle. Yeah. Okay, so this is what happened to most of the mines. So people would think, okay, so if it buckles, no problem, because you're looking at maybe several, 2,000 feet below. So if you have compared to the relative, this is the area that you're looking at, relatively, because the height usually is like 4 or 5 feet. Okay, so if you have 1,000 feet, there shouldn't be problem. But actually, that's not true because you can have significant subsidence when this collapse. Okay, so you quickly realize that this is a real problem. Okay, that's why most of those properties they are not sold. Okay, and only the local people live. Okay, now I also mentioned in China, so this kind of construction, you may get 46% of the coal out, and then the remaining you leave it. Yeah.
I think it's not right.
Oh, okay. Yeah. Okay. Yeah. Okay. But in some Eastern Europe and China, their mining technique is based on a technique that they use a machine. So in the back of the machine, the front of the machine is a big excavator. It digs, okay, and then in the back, they actually backfills the soil and then compacts. Okay, so you get more coal out. Okay, so you'll be excavating line by line by line by line. Okay, so you actually have materials that you backfill the mines. So that's the safer way to do it. Okay, and you actually get more coal out of the ground. Okay, so this is but in America now we're doing most of the time mountaintop blasting rather than longwall mining or deep mining. Okay, so surface mining has other related problems, okay, but you don't get this kind of subsidence issues. Okay, so this gives you some general sense, okay. Over time that we know that with groundwater fluctuations and different erosion mechanisms, the rock and the soil will give up their strength, and then it will collapse. And as it collapses, you have surface subsidence, okay. And in some cases, you may have sinkholes or sinkhole equivalents, ground void formings. Okay, so sinkhole formations are very common in these coal mine areas, okay, underground mine areas, and you can often see that even there are some areas the roads are so bad, the DOT, Department of Transportation, decide to completely remove themselves because it takes a lot of money to repair. I mean, the holes are huge, okay, so just to get the material to backfill takes a lot of time, okay, and a lot of efforts.
I think this sort of action happened recently in Chennai also, Professor.
Oh.
The sinkhole on the metro.
Yes, yeah, and foam.
But they were claiming that some underground tunneling metro was going on, and they immediately
blame
within 2-3 days.
Yeah.
But they don't know what was the root cause.
Okay.
PWD engineers were too confused.
Right. Yeah.
So it was a main road.
Uh-huh.
I don't know what place is that. You have you heard about that? Madhya Kailash.
Madhya Kailash. Okay. Uh-huh.
Suddenly, I think one car
drop in.
It got trapped.
Uh-huh. Yeah. So in Florida, we have limestone. In Florida, this is a very common problem. In fact, last year, the whole house dropped into a sinkhole. The biggest sinkhole, I think they have found maybe several hundred feet wide. Okay, but those are due to limestone, which is calcium based. So underground water actually eats out, and then you have karst formation. Okay, that's a more common formation of sinkhole. But sinkhole can be many reasons. A lot of roads that are not properly compacted, rain may seep under and then take out the soil, and you have another sinkhole forming. Yeah. Yes. Yes. Karst. Yeah. So karst is where you have a lot of limestone forming. Okay, and then those are the most likely candidates for sinkholes because the groundwater will eat the calcium. Because you will become weak acidic effect. Yeah. Okay, so you need to, if you're involved in this, you need to know your geological formations. Where are the likely? So this area is most of the coal mines were done. Okay, in the Black Warrior area, and further down here you have less coal. But you have seams, of different formations. Okay, so these are all lignite mines. Okay, and so the investigation is you go to the site, you look at the what happened in the area. Usually we would cover a wider area because you know that if it's a coal mine, the subsidence will not be just one hole. There will be something similar, So going around, checking out the whole neighborhood, looking for sinkholes is a very good indication. Okay, and again, the reason is because most of these are involve old mines, so they were not GPS based. So you have to be able to tell from the old map where the mines are. Okay, and then you go in there and verify, and then you usually do a geophysical testing. Oh. What did I do again? Oh, okay. You do geophysical testing, and then you create your hypothesis, okay, and then you validate with the mine map. Okay, so this
sort of sinkholes is possibly only in weaker soils.
Yes.
But strong soils, can we get this sort of effect?
Yes, there is possible. So if, especially if it's a compacted soil, man-made soil, so it's usually the grading is not so like natural soil. So when groundwater seeps through, it will wash them out. Yeah.
Once it loses that compaction,
it just go away.
the denseness is lost, then naturally.
Yeah, the problem will continue and continue and continue. Yeah. And so this is what we usually do, like algorithm. So you do you recognize mine subsidence, and this is the investigation process. Okay, so you know there's a damage to the properties, so you do the forensic investigation. You first do the visual inspection. You create assumptions and theories, and then you take the proper tools to do either geophysical testing, visual inspections, or do mapping correlation. Okay. And so in some areas, then the challenge is, can you distinguish between is it karst or is it mine subsidence? So now we're talking about shifting the blame. Okay, if it's mine related, then obviously you go after the mining company, right? And if it's natural sinkhole, then then they don't have a case. So this is where most of the arguments will come in. Okay, in the code fight. Okay, so in this case, the structure is actually on top of the mines. Okay, so you can see that we lay out the mine design. Okay, scaled it up to the area. Okay, and you can actually see how the building was on top of those. Okay, now you cannot go in and do detailed, exactly tell. Okay, this sinkhole must be on top, like what we were mapping here. These are all the identified sinkholes on the property. Okay, but some of them are on top of a pillar. The damage mechanism is too complicated. So by being able to identify the sinkholes, you pretty much nail the case. Okay, and then we do the surface wave testing method. Okay, so this is the property. Okay, and with the owner sitting in the front. Okay, and the property has a lot of, and this is actual Google map showing the location and the overlay with the coal mine map. Okay, and then you can see the building has already sustained the structural damage. So the cracking pattern, whenever you see a continuous crack, that means it's structural. Okay, something from the foundation must have happened. Okay, or the surface. And then this is the chimney. So you can see the chimney is actually bulging. So the differential ground settlements are causing many, and the chimney is separating from the remaining of the wall, the brick wall. Okay, and then you see a lot of sinkholes on the ground. Okay, so being able to go to the site and then look for those sinkholes becomes critical. A single sinkhole may not tell you a lot. Sometimes those sinkholes, especially the small ones, may be snake hole. Okay, so big snake lives in there. So you have to be careful. You don't use a rod to disturb the snake. Okay. And so when we do the SASW testing, notice that the curves are not as clean as some of the cases that I showed you before. And the reason is because the disturbance of a mine settlement, okay, it's actually very complicated. Okay, so we're not looking at a sinkhole as a big void. Sometimes it does happen, okay, but most of the time it was the big rocks start collapsing, and then you have a lot of debris, rocks, smaller rocks, and so forth, okay, until it gets to the top. So the analysis of those results are usually not as clean as an actual sinkhole due to karst. Okay, so and if you have ever been to a cavern, underground cavern, see the the dangling limestones and so forth. Those are the bigger sinkholes that will form over many years, hundreds of years. Okay, and so nature's karst formation, the sinkholes will be much more well defined, but mine settlements are much more disturbed, and as a result, you see our geophysical data becomes more disturbed. Okay, but still, looking at this data, you can still create some kind of opinion. Okay, so for this particular case, and this is how we usually do, we will define our opinion. So we found very shallow, stiff soil within 10 feet. In other words, the reason the building hasn't disappeared is because the surface soil has not fully disturbed. So they are still stiff. Okay, but then we cannot, we don't have well-defined sinkholes. Okay, and so the fact that the test 1 and 2 are consistent shows that the site has stability. Okay, we don't envision the building disappear anytime. There is a trailer nearby. So other than the house, there's actually the owner has a trailer. So trailer is a pre-engineered house, kind of like the containers on the truck. Okay, so in America, people use that to live in. Okay, and that container actually has one end of the support settled. Okay, so we know that it's sinking. So we know the problem can be significant. Okay, and then because the site is on top of we prove that it's on top of a coal mine. So we pretty much conclude that that is the cause of all the problems to the structure. Okay, and this shows our soil testing. This is how we lay out the test. Okay.
Now, how to rectify this effect, Professor? We can go for some lime stabilization process.
No. So for this kind of problem, you need to drill a hole and then grout. Yeah, the only way to solve the problem.
It can be either lime grout or cement.
Yeah. Now you can also use micropiles. Yeah. So micropiles are not like the real piles that are big. Micropiles are the machine for micropile are actually very light. So you can put it close to the building and then put the piling down. Okay, you can make many piles and then kind of supports the structure. So you will not settle. But still you are not, the long-term solution is still grout. Yeah. But you have to go into the mine shaft and then grout the mine shaft. Yeah. That takes a lot of concrete. Yeah.
Because we don't know what would be the depth.
You don't, You don't know, yeah. So in that case, then you need to drill a big hole underneath, yeah. So this is, so we spend a lot of time using Google Map and then put the mine map on top, okay? And because the old mines, as I mentioned, they are not GPS georeferenced. So being able to match them is a very challenging work, okay? And we look for features such as this is an existing river. We know the river was there even when the mines were active, okay? So using the mine map, we actually found the river feature on the mine map. Then we are able to tell the scale of both the mine setting, okay? And this is the analysis. So you have a building damage. You found there is a building damage. The first question you ask is it within a mine zone? Okay. If yes, then you pretty much don't have to argue anymore, because usually the lawyers has a strong case claiming that the building was collapsed because of mine. Okay. And then of course you can do geophysical testing to determine if there's mine void. If there is a mine void, then your case will be even stronger. Okay. But typically, we don't get to see that because this is another thing about geophysical testing. If you have disturbed soil, then the wave cannot travel so far. Okay, and also when you do the geophysical testing, it's very unlikely that you can reach that depth using surface impact. Okay, if you wanted to tell where are the mine shaft, then you really have to use some other innovative techniques, such as a passive, just by listening to the ground vibration and detect how deep the mine void is. Okay, and then if you have any other evidences. Okay, so if you can find a mine entrance nearby, that automatically tell you this is a mined area. Okay, and then you usually have a basic two conclusion. Is it due to abandoned mine collapse or due to not for mine collapse? You only have two solutions. Okay. And this is another case study. So this case, the demonstrations to show you. So this is actually a big manufacturing plant. Okay, and they wondered if they're going to install a heavy machine, but they are worried that the foundation is not strong enough. So we do the geophysical testing for them to see if the foundation is competent. Okay, so this is the general scenario. So you have the building, you have the working area, and where they're going to put the heavy foundation, heavy machinery. And then you have underground water pipeline, and then there are grassland and parking. So this is a constructed site. Okay, and the goal for us is to go in and see if there's anything that's happening underneath. Okay, and so we did the soil testing. So the purpose of showing you this is to show you the signal processing process. Okay, so you have two sensors, and then you can construct a phase diagram. This is called the phase diagram. Okay, and based on the phase diagram, and all these are based on frequency, so you can back calculate the depth and the wave speed, okay, by using the angle phi. Okay, so this represents one wave speed, another wave speed, another wave speed. Okay, and then using the software, you can block off all the noise data. Okay, but this technique is not straightforward. You have to assume the soil property. Okay, because when you do the testing, you're based on measured wave speed, right? So everything else you have to assume. So you have to assume the soil properties, and you also have to visually see, like here we block it out because we can't really see a cycle. Okay, so a lot of these are manual analysis, okay, based on the experience and so forth. Okay, so this is the reason I present this is, I have not yet encountered a case where the court would scrutinize, saying that, hey, your analysis is wrong. Okay, but if they were to bring this issue up, then it would be very difficult for me to explain why do I recognize this as the cycles when all of this I ignored. Okay, yeah, it's based on experience. Okay, and so that can be challenging. And as you can see, the results are very, very disturbed. And this is velocity versus wavelength. Okay, so in geophysical testing, the typical procedure is you do the vibration sensing, right? You assume the distance between the sensors. So for deeper soil, you move the sensors further, so the horizontal distance becomes larger, and then you have to use a much stronger force. Okay, and once you get the signals from the two sensors, they are related by the distance. Okay, and so you have to calculate the transfer function between the two. Okay, once you create a transfer function, then you have to do what we call the forward modeling. In other words, it's not straightforward. Okay, so the procedure is when you do the testing here and here, you kind of generate a set of curves. Okay, and then you construct the velocity versus wavelength. Okay, and then you do the forward modeling. You assume, hey, I have this soil. Okay, and this is density 1, density 2, density 3, density 4, and so forth. And then you calculate what is the profile, and then you use that wave speed to match this line. Okay, so you quickly realize that this is not something done overnight. It takes days to do this processing. Okay, and then because you have to match this line versus this line, okay, your assumption becomes a inverse problem, meaning I can assume 500 lines, or I can assume 5 lines, or I can assume 50 lines. It becomes an optimization problem, okay? And you cannot simulate so many times, right? And if you assume 500 lines, every one is like only a few inches thick, it's not reasonable. So it's based on a lot of your experience, okay? And so this kind of analysis, it gives you some data, but it's mostly for reference, okay? And it's not a strong evidence, okay? It is an evidence, but it's not a strong evidence, okay? And so you can see this is another set of data. And my student and I will argue, should we throw this data away? Because they are so far away, it's not easy to match a curve. Okay, but, you know, we would debate. And then once you create the wave and velocity curve, it looks like this. Okay, this particular curve alone tells me that the pavement on top is very strong. Okay, and that is why you suddenly have this singular effect. Okay, and this is our final analysis. So you can see that the slab is very powerful, but then after that you have consistent soil for about 1,000 to 1,500 feet per second wave speed. Okay, so this is wrong. Something is missing. This foot per second. Okay, it's wave speed. And so in summary is that we demonstrate the slab is very strong. It's almost like a rock. Okay, and the actual is the slab was about 5 feet deep. So they have anticipation that there will be, and then but the soil underneath is clay, because it's about 1,000 feet per second. So we think it's clay, and also because we kind of know the area, and we have not found any bedrock at 40 feet. Okay, beyond. Okay, so they ask, in this particular case, we just provide the data. We didn't tell them should you or should not you build your machine on top of this foundation. Okay, and let the geotech engineer make that decision. Okay, because this data alone is not going to tell them enough information about what the foundation will be. Okay, so in order to actually determine if the foundation is competent for their machine, I actually have to calculate how much the machine weighs. Okay, and then what kind of boundary condition, what kind of support system they design for the structure, and then we have to do different tests by using a shaker to vibrate the ground so that we can determine how much it will actually influence on your vibration frequency. Okay, so all these are, again, additional work that we could have done, but then the client will have to cover more money because then I have to rent a shaker and do all that testing. Okay, so again, not a perfect solution, but we give the client sufficient data for them to make a decision. Okay, and so by telling them that the foundation is stiff and then the soil underneath is clay, you can use Richard Woods and Hall, the foundation vibration classic textbook, and they have solutions that you can go and pick up whether that would be able to qualify for this kind of design. Okay, so I think most Indian students have structural dynamic, right? So in structural dynamic, you have the single landmass model for elastic foundation problem. You can build one of those models based on the weight of the machine and assume stiff spring constants. And then you do a bunch of analysis and determine, whether this will support, that will cause a disturbance from the vibration. Okay. Now going to a famous case. Okay, so this is the San Francisco Dam in San Francisco National Park, California. Okay, so this dam is one of the first concrete.
San Francisco is different and San Francisco is different.
Yes,
It's a
yeah.
different place.
No, actually, San Francisco is the short of San Francisco, okay? But it's not the same as San Francisco. Yeah. So this area is actually closer to Los Angeles than San Francisco. Okay. And this dam was designed, built by a very famous dam engineer at that time. You know, we're talking about 1920s. Okay. His name is William Mulholland. Okay. He is not a trained engineer. Okay. And you have to remember, in 1920s, in Europe, they built a lot of concrete dam. But in the U.S., at that time, we only have earth dam or rock dam. Okay, so William Mulholland, you know, and you see in history many, many times the Americans trying to match up to the European technology. So he started building concrete dams. Okay, even though he's not a trained engineer, he's self-learned, and you know, he had definitely no qualification for concrete, but he started designing concrete dams. Okay, so he's a very hardworking. And he's not even a geologist, okay? And so all of this, lacking of his background, actually go into the forming of the theory of why this dam fell, okay? But this was a famous dam at that time, and just give you a little background. So California, even though it's on the west coast of United States, it's actually very dry. It's more like a desert, okay? So water has always been a problem for Los Angeles. Okay, pretty much the whole coastal area. Okay, and so to supply water to California, early on in the turn of the century, of the 19th century, they actually already have grand plans of building a lot of man-made canals to supply water. Okay. And so this is actually part of the Owens Valley Aqueduct. Okay, so I have driven over. Those are big aqueducts they built. Okay, and it's actually, you know, bring the waters from all the way up in the mountains down to the LA area. Okay, and so the dam was actually built. San Francisco Dam was actually built as the first concrete dam in the U.S. Okay, and then the dam is trying to.
This was before Hoover Dam.
Oh yeah, way before Hoover Dam. Yeah, way before. Yeah. But William Mulholland, you know, wanted this grand project. He was at the time the head of the Los Angeles Bureau of Water and something else. So he's the head, and he do all the design himself, you know. So he studies very, very hard. He self-learned concrete technology, self-learned geology, and so forth, and so forth. Okay, so this is the remaining of the dam today. Okay, so, you know, all that grandeur monuments is already gone, and you only have this. Okay. But it is built in the San Francisco Canyon. Okay, so the idea is the dam would flood the entire canyon. Okay, and then it's very close to the LA Aqueduct. Okay, and has very unique topology, and also from a geological sense, it's close to several fault lines because it's in California. Okay, and the rock type is the Sespe conglomerate rock and a lot of mica schist. So if you know a little bit about mica material, they are weak in shear. Okay, so they have a shear plan. Okay, so usually this kind of rock will fall in a very distinct shear surface. Okay, and this is the construction of the dam. So it is the Bureau of Water and Power. Okay, and it's a concrete gravity dam, and it's an arc dam. Okay, it has a height of 185 feet. Actually, this is another thing that people criticize. So original design was 175 feet, and then when he submitted the plan, I think a year before the construction, he himself added another 10 feet. Yeah, so become 185 because at that time there was a discussion about how much capacity they actually need. So he increased that height and then increased the capacity. So the reservoir has 39 million meter cube of capacity. Okay, and also on top of increasing the height, he also added the wind dike. Okay, on the sides. All of that was just added last minute. Okay, and so the dam was constructed between 1924 and 1926, and it was filled in 1926. Okay, so right after the dam was constructed, they start filling water in, and it has problems from the very beginning. Okay, so a lot of cracks start happening, and then there are some leakage starts showing. Okay, and so Mulholland actually would personally go and inspect every of those cracks and seepage. Okay, and then determine if it should be repaired. Some of the repair work later on would criticize that was not effective. Okay, but he was very thorough checking on the scenario. Okay, so this is just to show you the perspective from a geospatial sense. So this is the Los Angeles metropolitan. Okay, the San Francisco Dam is right here, and so this is the San Francisco Valley area. So the intent was to flood this entire area. Now there's an existing dam not too far from this that was built after. Okay, and then it floods this side of the valley. Okay, and the distance from here to here, I think, is about 40 to 50 miles. So it's very close. It was built intended to help Los Angeles water supply. Okay, and this is the remnant of the San Francisco Dam. Okay, and this is the existing dam that is very close to it. Okay.
So when did this dam fail, sir?
1926.
Oh, it failed immediately?
Yeah, immediately. Oh. Yeah. Mm-hmm. Okay. This is Google again. Zoom in to show you. You know, right now you can't even see the shape of the existing dam at all. You know, time kind of erased many of the evidence. Okay, except for those rubbles that was remaining from that failure. Okay, so this was the actual dam right after it was built, but you can see there's already a big leak. A big seepage. I think it was like 75 gallons per second water's coming out. Okay, 75 gallons not a lot, you know, relative to the size. But you know, yeah. Well, actually, a lot of concrete dams after you design build, they will have seepage. They will have, so you have to do repair. Yeah, but causing a drastic failure was not very common. And you can see this is already, they already start backfilling the water behind the reservoir. Okay.
So only the shear, it is only due to the shear.
We don't know.
It's a geotech failure.
It's a geotech failure, but there are many theories behind. Yeah. And this project was done in a day when we don't have forensic engineering. So there are a lot of inspections, but you know, there's no strong conclusion. Everybody has many theories. Yeah. And even the official solution was not, you know, many engineers doesn't accept the official answer. Yeah. But you can see that, you know, this is what it was designed for to.
So how did he face the situation? Any history about that? When such failure has occurred,
oh,
he should be answerable, right?
He lost his license and he retired right away. Yeah, he never worked again. Yeah, after this. Yeah, so it's the implication is many more. Yeah, so this is just to show you. So I actually superimposed the previous dam image to the Google Earth 3D just to show you the magnitude. So you can see the behind all this are supposed to be flooded. Okay, just to give you the perspective. Okay, and this drawing is from the technical report. So people show where are the cracks. Okay, and the unfortunate thing is some of the cracks actually tie into the rock formation. So then the question is it concrete problem? Is it rock failure problem? Okay, and also there are many fault lines in this zone. Okay, and so there are a lot of criticisms, but so there are many leaks and cracks, and so this is a picture. 17 liters per second was discharged from this one single crack. Okay, at that time, so they know there are problems. Okay, failure happens at 2 years after. Sorry, it was 1928. Okay, when they are still feeling behind, and then it was late night. And 430 people, basically a downstream village was completely washed away. Many people died. Yeah. And because it happens at late night, nobody actually witnessed what happened. There's a watch person that went by, and he said he heard some really loud noise. Okay, and but because it's dark, so he can't see exactly what happened.
What about mica, Professor? When mica substance have some direct contact with water, how it behaves?
I think mica over time will swell because I think there are some sodium, in the material.
Might be the cause of that.
No, that is one probable. Right? But mica is not. They don't form like large rocks. Yeah. They usually are pockets of materials, but it usually indicates.
Area is fully surmounted with mica.
A lot of mica in that area. So there are many theories. Okay, one theory is because at that time there are people who protest because fighting for water. So at the time that he is filling up the dam, they actually have people. Excuse me. Request water draining for power, for apply water, and for power generation. Yeah, thank you. And then there are others. There are people who protect the fish, and so forth. So there are some evidence that supported. Oh, okay, I got it. Yeah, thank you. But then there's also contradicting evidence. So some people say it's earthquake, but there's no earthquake. So there are many theories that are being proposed. And there are some dynamiting. So because this is not the only project ongoing in that area, so there are some other works related. So people were claiming that because of that work impact on this area. But most important is, at that time, the Americans really don't know much about concrete material, especially for concrete dam construction. So this again, there are some questionable issues also. Okay, so one of the theory was at that time there was a strong debate about uplift relief. Okay, so uplift relief is the uplift is due to water pressure from underneath the dam. Okay, so what can you design the dam so that the gravity would prevent the mine from experiencing uplift? Is at that time there was no laws dictating, how if you should provide any kind of provision. Okay, and so that was one of the arguments. And then many people were talking about, the dam wasn't wide enough, don't have enough gravity weight and so forth. Okay, and but he did his work was, so he's even though he's not a qualified engineer, but he's a good engineer material person, so he did a lot of calculation, and all his calculations available for people to evaluate. Okay, and then another theory is that the construction was not good. Okay, so there are a lot of evidence. One is later on when people take the concrete material, they felt that the strength of the concrete was not strong enough, and there's no expansion joints, contraction joints, there's no reinforcement. Okay, and again, people argue about uplift relief. Okay, so there are many criticisms towards him about his design. Okay.
But it's like an earthen dam only.
Huh?
Yes.
Yes.
Dam is an earthen dam.
Yes, yeah, like the earthen dam.
In that case, concrete strength is not predominant.
It's more like a gravity effect, right? Rather, yeah. But then the concrete should have sufficient material to prevent seepage.
Only thing is we have to arrest
the cracks.
Porosity.
Yeah.
That should not happen.
Porosity, yes.
Porosity
Yep.
of the concrete.
Right. Yeah. Yeah. So there were but these are all the theories people bring up and criticize his work. Yeah. And then, of course, his lack of background in geology is also another thing that people criticize. They claim that he didn't do enough investigation in the geology before again, those materials were blamed for failure.
Conglomerate is a sedimentary rock category.
Yes, it's sedimentary. It's not like volcanic based. Yeah. So it's not strong rock, yeah. And then but of course that area, there's no history of ancient landslide and stuff, yeah. Okay, and then people propose many other theories, such as why the west abutment failure initially. Okay, so again, insufficient geology, inadequate excavation of the incompetent rock, for the forming, and then the location of the dam blocks after the failure is some of those arguments. Okay, so the failure mode of the later on we'll show the picture. Okay, it's actually not the whole dam being washed out. There are some columns left of materials left. Okay, and so that leads to people come up with many again, like the Mollyvakum case. How it fell, the shape of the remaining material always intrigues engineers and make people propose different suggestions. Yeah. And this picture shows that before the dam was completely collapsed, they actually go in there and look at the cracks and failure and so forth. And there are many arguments. All these are supporting evidence that people suggest that they have.
It's very significant. The failure.
Yeah. It is. Yeah, it's very large cracks. Yeah. And this is the remaining of the dam. Okay, and so after that, of course, there will be a lot of changing of laws. Okay, so dam safety was start raised about this kind of dams. Okay, and then retrofits. How do we retrofit dams? Were discussed, and then of course uplift force relief is one thing that now we have a provision against that kind of failure mode. Okay, so and then of course Mulholland, as I mentioned, he lost his license and he lost his practice. He basically retired immediately after the case. Okay, and I think his last days are very sad. The guilt of having so many people killed was carried with him forever. Yeah. Okay, that's Mulholland in not his later days, but when he was aged. Okay, and this is really all that's remaining of the dam. Yeah, and of course today if you go, you only see this part. All the rest are already eroded and disappeared. Okay. So this is a very famous failed geotechnical case, and as I mentioned, geotechnical cases are usually very complicated, very difficult to fight over. Okay, but it happens. Okay, and one of the problems that I always criticize about construction residential is people are not willing to pay for initial geotechnical investigation. Many failures could have been avoided if they only have a few more boreholes, okay? But that, boreholes are expensive. The money that people spend on starting the foundations before the actual construction was less than 0.1% of the whole project cost. That is not sufficient. But, people are always trying to cut corners. And geotechnical investigation is usually one of those areas. And so from that perspective, geotech has less reliability than structural. Okay, both from materials more homogeneous and also from the uncertainty in your knowledge of the site. Okay, so those are very critical evidence and discussions that we need to have. Okay. So interestingly, at the same time of building the famous St. Francis Dam, they actually are building another dam called the Mulholland Dam. So it was named after him because he's such a well-known, distinguished engineer. They're actually building a dam named after him. Okay, and you can see it was built about the same time. Okay, and this is within LA City. Okay, and it's another concrete dam.
This was done by him itself, Professor, or somebody else?
I think it was designed, built by himself as well. Yeah, but they named after him. Okay, and then of course after the San Francisco Dam fell, people start having questions about this dam.
No, but this is 1923, 1924.
Yeah, before. About this. Yes, yeah, before that one. Yeah, before. Because almost is about the same. 26, yeah, built in 1926. Yeah, but then after that dam was fell, people worry about this dam. So what they did is they actually asked them to put a lot of dead weight on the opposite side of the dam. Yeah, so this is the lake side, the upstream. The downstream they actually shored it up with many material, worried that it will fail. And yeah, this is the last picture. So even though they maintain his name on the dam, but exists. Yeah, this never had problem. No problem. Yeah.
That is, as you said, it is the geotechnical issue. This doesn't have any mica or...
well, no, because it's close by, so it may have, but it doesn't have that much capacity. Yeah. Yeah, and not as big as the other dam. Yeah. So these are interesting geotechnical case studies that just to show you, the extent and also the complexity of geotechnical forensics.
How about Hoover Dam, Professor?
Hoover Dam has no problem. No problem. Yeah. In fact, Hoover Dam, he named after Hoover and was very proud of that project, President Hoover. Yeah. The entire project is very unique. It has many engineering achievements on the Hoover Dam. But also the Hoover Dam, if you go there, so one of the issue when we build the Hoover Dam is because the existing fault lines are very close to the dam. So the dam had not failed in any ways. Yeah. But the building of the dam was under a lot of stress because it was...
That was challenging.
Yeah, very challenging. Yeah. Yeah, I have a separate set of notes on the Hoover Dam. Yeah. But because it didn't fail, so it was not a forensic case.
Not even single repair work has done.
Yeah. Yeah. But actually, now the argument about Hoover Dam is it still necessary? Because now the Colorado River has dropped. Yeah, so there's not enough water. Yeah, now it becomes a fight between Nevada and California because of the Colorado River. Yeah, dam.
So they are planning to...
No. Nobody would dare to suggest, but they question, why should we have a dam? Yeah. It's not serving as much as what it used to. Yeah. Now, another very important thing is, because energy is not a big issue today. Okay, And in America, we have not built dams for many, many years because of environmental issue. Okay, but now because of we're trying to avoid using fossil power generation, so hydropower is coming back. Okay, so we may be seeing more dams being built now. Okay, and of course then you go into the same argument. Are those engineers knowledgeable enough to build dams? Are they, like Mulholland, want to challenge himself and build some dams that he has never seen or done before? So those are really critical questions because of the change of the politics and also the energy environment. Any questions about this?
You can interact any geotechnical aspects.
I think most of the kids are structural, so yeah.
What was the height of the dam?
The height of the dam, which one?
The
The old dam, it was 175 feet, and then they built this particular one.
Yeah.
Oh, I don't know. I don't know the detail about this one. Less than, yeah, way less, yeah.
50% half of that.
Uh-huh.
Not even 90 feet, I think.
Yeah.
Seems to be like.
Right. Yeah. It's a much smaller dam. Yeah.
That is actually 175, the earlier dam.
Yeah.
Later on, he increased the height suddenly with 10 feet.
Mm-hmm.
Whatever the approved one is only for 175 feet.
Mm-hmm. Yeah. But he himself approved it. He's the head engineer of the whole. Yeah.
He's the authority.
Right. Yeah. We are not in those day and age, but this is a very high visible case. Yeah, I bet you the newspaper, his name is all over every day. Yeah, because of this argument. Yeah. So, I have never been involved in any famous case. So, I have not been a star witness or, star expert in any capacity. But if you were one day being called to such a role, can you imagine the pressure on you?
Absolutely.
Absolutely. And even in this day and age, when the social media is very popular,
In that way, we should be very, very careful.
Absolutely, yeah, very, very careful, yeah. Mm-hmm.
Because the media, all the world will be watching us.
Yep.
What he says, what's his views.
Yeah.
We have to be very careful in releasing anything.
Right. Yep. Mm-hmm. Yeah. Yeah. It's not easy for this kind of case study.
I don't know how will be the political pressure influence in the
Oh,
United States.
yeah, it's very
dominating.
Absolutely, yeah. It's in some cases dominating as well. Yeah, like the World Trade Center after the 9/11. Oh, the pressure is very high. Yeah, especially to the investigators because people criticize them as well. Yeah.
One set of people will be opposite.
Yep.
Who will be who
Yeah.
has expertise in the same area.
Right.
When we present something, he criticizes.
Yeah, and they don't criticize to your face. They write papers and they go to conference and say you're not good. Yep.
That's very terrible.
Yeah, but the more important problem is, like the Pentagon case. So Pentagon case, the airplane runs into the Pentagon, right? So you can literally see holes of the when the fuselage ran in, and then so you literally see holes because it has many walls. So the holes getting smaller and smaller, but you don't see the whole integrate of the airplane because the airplane is already disintegrated. So how does it form those holes? There are a lot of still unknown, and just because you cannot explain everything, people criticize you. Yeah.
One general question, Professor.
Yeah.
As far as this geotechnical investigation is concerned, when we go for any multi-story building construction or anything, when we do some geotechnical testing, the soil test.
Yeah.
They say that if the soil strata, go till the hard strata. Go till the hard strata and design your foundation. Like that, in case if the soil is weak.
Yeah.
If the bearing capacity.
Yes. Yeah. You drew it to the bedrock.
Drew it to the bedrock.
Right.
But how we can validate the strength of that bedrock, Professor? Sometimes all hard strata.
No. There are methods. Yeah. So you need to. I don't know how much rock coring you actually do here, but when you drill it, after your soil is removed, then you need to drill into the rock.
Into the rock.
Yeah.
We have to see the
And then the rock qualification is another set of science.
rock
Mechanics. Yeah, rock mechanics. Yeah. So yes, you can determine that. Yeah. Yeah. And also, not just drilling to the rock, but also how deep you need to pile.
Suppose
tie
I
it
have a situation like that. My rock, that rock is not a granite material. It is some other thing. Let us say it is not neither a sedimentary category or a metamorphic category in between.
Right.
And we are not satisfying that required bearing strength.
Capacity. Okay.
In that way, if I want to plan a 40-story building or a 50-story building over there, what will be the solution, Professor? What can we do for that case?
Okay.
If the soil bearing capacity is a bit poor.
Yeah. Then you design the piles to go deep.
Say let us say it is 20 meter deep. We got the hard strata in the 20 meter deep, but the hard strata is not satisfactory. So we need to go deeper.
Yes, you go deeper. Yeah.
Might be we will.
And or add more piles.
Okay.
Yeah. So in pile design, there are several methods to strengthen your foundation. If you cannot go going deep, of course, but going deep only mean certain things. Yeah. So if you have a high-rise building, okay, of course you wanted the piles to go into the competent rock. Okay, so the design of the pile group becomes critical because once you go to a certain depth, you're approaching fixed end, right? But if you go way deeper, then there's no purpose. Yeah. So you go to a reasonable depth, and then if they are not strong enough to support the structure, then you add more piles. Yeah. And then also the pile group effect. You need to compute. Yeah.
Have to group the pipes.
Right. Yeah. There's group effect.
Can we do any strengthening technique at the base and the bedrock? Is it possible, Professor?
Grout. Grout. Yeah.
Lime grouting.
Yeah. You can grout to make the rocks more stronger. So sometimes you can blast up, dynamite blast, and then remove the material and then put grout. Yeah. High strength concrete to grout it. Yeah. So there is possibility of improving the design.
And we need enormous time to allow them to set, and then after fully set, we have to go for the construction.
No, usually the grout will be settlement is totally different kind of issue.
I need them to set
the concrete setting. Not necessary, because it takes time to build up, right? So usually when you have the foundations already built, sufficient time, at least definitely more than a week or so.
Okay.
You already reached 80% the strength. Yeah, and then you start building up the top. So usually by the time you start building the top, your foundation is already set. Yeah. Yeah.
That is the.
Yeah.
Even the friction capacity is okay. Why you want to come and anchoring?
Because the premise is high-rise building.
It's not adequate to take care of take that entire load. So we have only this solution.
Yeah. I mean,
it is quite critical, so that's why I asked this
Yeah.
question to Professor. What is his views about that?
right. I mean, even if you have even if you have soil that has strong enough, so piles are, especially for deep foundation, the piles are due to friction resistance and the pile tip resistance, right? So even if you have sufficient, because of you are a very high-rise building, 20-story and above, you wanted to tie down to the bedrock as much as possible. Yeah.
Negative skin friction.
Huh?
Negative skin friction is
Yes. Yeah. Negative friction. Yeah. You mean direction? Yeah. No. Your dead load is coming down, right? So negative friction. Yeah. By friction pile. Yeah. So when the pile is down, when the weight is pushing, the friction is preventing the pile from settling. Yeah.
When you are doing offshore structure, offshore design,
Generally
it is very hard to make the bedrock.
Yeah.
So generally they will prefer to go with only friction pipes.
Yeah.
It's not a solid pipe.
Right. Yeah.
Hollow circular.
Right. So you have to have a high you have to have more piles and then have a higher factor of safety. Yeah. Yeah.
So in case of driven piles,
Driven piles. Yeah, all these are driven piles.
when we are making it not in an eccentricity,
Yeah.
if we are not driving, will it affect the pressure bulb capacity?
Yes. Yeah, it will. Yeah, but there are standard design approach to calculate that. Yeah. Yeah. Dynamic effects for the driving piles.
While driving the piles, if
Uh-huh.
it's going in a straight way, it's no problem, sir. But while we are driving it, if it is going some angle, then we are
Yes. Yeah. Or again, there are calculations that you can correct that effect. Yeah. Yeah. It's all done by software. No.
Suppose if I get a farmland,
Mm.
but that is unfit to go for farming.
Uh-huh.
And instead, we can go for some building construction.
Yeah.
Normally, farmlands will be low-lying
Yeah.
level areas.
Right.
So, and the soil structure is also very poor.
Right.
We have enormous water table. The water table is well within
Yeah.
3 meters,
Uh-huh.
3.5.
Then in those cases, you need to treat the soil.
Treat the soil.
Yeah. For example, you need to, like rice paddies and, area where you have heavy farming. If you would convert them to industry or convert to building, then you need to treat the soil like, put heavy weight on top or scrape the clay on the surface or, use sand drains to drain out the water first. You need to spend 3-4 years to prepare the land for those kind of construction. Yeah.
So if it's black cotton soil, we cannot able to do it.
Huh?
If it is a black cotton soil, then we cannot able to do it.
Black cotton soil?
Clay.
Clay.
Expensive soil.
Oh no. You take them out. If it's not too much, you remove them.
If it is an expensive soil, we cannot able to treat it, right, sir?
Right. Yeah. Not recommended, but there's always soil treatment you can do to improve on the condition. Yeah.
Clay and other things.
Uh-huh.
Column settlement, right? You can go for pile foundation. At the ground floor, generally what we will do, we will not put slab.
Mm.
We will fill it, we will take a material. There you can construct a slab. So automatically the consolidation below the slab element will not be a problem.
Mm-hmm.
Foundation can be done with pile.
Mm.
Before that pile on ground floor itself, we will be having slab, beam and slab. We will have a beam and slab elements. So automatically the load transfer occur directly. We are not allowing the load transfer to occur directly to the ground. Even if it settles by some amount, it's not a problem, right? Our slab will take care
The
of it.
beam and slab will take
Yeah.
Mhm.
Actually, while you were describing that, remember CN has a case study,
Case in, I think, Cochin somewhere.
Kuching? Okay. But didn't CN did a very interesting case in Vizag College, or there's a
Care college.
Care college.
Care College, yeah. So the basketball arena,
Yes.
yeah, the groundwater pumping, yeah. So you have a groundwater pumping case. That's another very Very interesting case. So the ground is sandy soil.
The pond was nearby.
Yeah.
Because of that,
The water starts
the
to
pressure
coming
was very
out.
heavy.
Yeah.
It was like a jet pump.
Yep.
The water.
Yep. Yeah. So that was a very interesting.
Then he did some beep holes and he allowed
Right.
drainage system.
Yep. Yeah. And then you put heavy weights
Heavy
on
weights,
top. Yeah.
And it was rectified. That was a very interesting.
Very interesting case. Yep. Yep.
Sometimes we don't know what is the root cause of the problem. But if we go a little bit deep,
Yeah,
the concept
I mean,
will be very simple.
Right. Yeah.
You can rectify it very easily.
Yes. Yeah. So I often ask CN. So his problem-solving technique is very creative. You know, I'm always curious what Western engineers would do. Yeah. Like that particular case, I will probably find out where the groundwater is coming from, and I will cut that off, right? Instead of just solving this problem. Yeah. But he solved the problem, so yeah.
Ultimately, that should not come.
Right.
Should
Yeah.
not seep out. So
Yeah.
he gave the provision.
Keep the drain.
Let the water keep draining.
Yep. Any other questions? Yeah. Good. Yeah, I know that geotech is probably a little bit odd, but
Sir, but we should know.
you should
certain
know. Yep.
things. We cannot fully rely on geotechnical experts.
Right.
Also.
Yep.
Even they themselves, they don't have answers
Right.
for certain questions.
Yeah,
When we
absolutely. Yep.
pose, that is the thing. At least
Yeah.
we can have some slight knowledge
Right. Yep.
on that.
Yep. And of course, I only demonstrate one geophysical method. The more common method is you drill a hole and then you put the sensors down the drain. Yeah. And then you use stress wave to detect change. Okay. So, but those techniques are much more expensive. For only high-profile case, they will allow that.
How about electrical resistivity method?
Electrical resistivity methods are very good in soil, not for rock. Yeah. So soil, it's very good in determining the capacity of the soil density, and so forth. Yeah. Now, that's one technique available that can be done. Yeah.
Would be cheap and best.
Cheaper, much cheaper. Yeah. Yeah. Any other questions? No. Okay. As a reminder, your homework is due today. The point cloud analysis. How many of you have finished? Oh,
Actually, that file was not opening.
the file is not opening. You should have asked Navneet. Yeah.
Is that to help you, right?
Yeah.
They already shooted you a mail, whatever the.
I installed as well as I downloaded, but that is a FLS file. That is unsupported.
No, FLS file supports, by Cloud Compare, yeah.
The latest we will tell them to submit by 19th.
Okay.
And tomorrow they can give their seminar presentation.
Right.
The case study presentation you get ready by tomorrow.
Yeah.
The groups, so that we can have a review immediately after lunch. We can have, and Thursday you can finish your
Homework. Okay.
assignment.
Yeah.
If there is any doubt, you please ask Navneet. He is there
To help you, yeah.
7 p.m. he is there.
Yeah.
So you can sit with him, or you can come over here,
Yeah.
and you can have a discussion with him, or
Right.
you can go to the guest house,
Yeah.
and you can have a discussion.
Yeah. When you come to lunch, usually that's a very good time to ask some
So
questions.
if you have doubts, you should not have kept with
Yeah.
you, so that you could have. We are in an impression that you have completed.
Yeah.
So this is the thing. See, when he is here, you get trained to that software, used to that, so that it will be useful. If not for some other application, it will be somehow it will be helpful.
Yeah.
Okay, once I'll have studied this technique, so it will be somehow it should be helpful.
Yeah. I can guarantee you when you guys go out, within 5 years, you'll be starting to see people submitting point cloud. So knowing, at least get a little bit, we're not asking too much, just a little bit of experience would be sufficient for you to manage those kind of data. Okay, so that's why we insist on you doing this homework. Okay. Yeah. Any question, please ask Navneet. Yeah.
So Friday's lecture alone, we will start somewhere around some 40 minutes advanced. Normally we have it around 11 a.m. So we will start around 10:20 or something, 10:15 or 10:20, so that we can wind up before 12:15 or something. And then half an hour we will have a small objective test, whatever you have gone through the slides and everything is there. The questions will be based on those things. Your materials is given to you, so that we'll have it will be like 30 odd objective questions. It's not, you won't require less than 30 minutes. So we'll have a 30 minutes quick.
25 questions.
25 questions you can take for 30 minutes.
Yeah.
And then we will discuss for lunch. After that, we'll come and we'll distribute the certificates and we'll honor the professor.
Yeah.
And we'll close the program after our lunch. So by that time, I think these 2 days will be little bit, lots of works you are, and tasks you are about to complete it. So please get it versed as much as possible.
Yeah.
So then we also will be having satisfaction that you have some amount of knowledge.
Yeah.
The purpose of this course will be fulfilled. That's another. Any doubts, you are welcome. And if you have any technical issue, doubts and other things regarding the forensic in the slides, you can interact with professor. Or the practical doubts, whatever in the software, you can contact Navani. If there is any discrepancy in the assignments, if you are unable to follow certain terminologies, you are free to ask.
Yeah.
So I think
okay,
that's it.
We will conclude here, but we will stay a little longer for you to ask Navani questions.
Sure.